Hello everyone. Today in this video we will discuss about pharmacologic fundamentals. So before I begin this video, have you ever wondered why a painkiller you swallow takes 30 minutes to work, but on the other hand, if the same drug is injected in your veins, it works in matter of seconds? Or if you double a dose, it always doesn't double the effect, right? And two drugs which are taken for treatment of exact same condition or disease, but one requires different safety profiles, right? So to understand this both, we will discuss about two branches of pharmacology. The first one is pharmacokinetics. So basically pharmacokinetics means what body does to a drug, and the second one is pharmacodynamics, means what drug does to the body. So in this video, we will build a solid ground up understanding of both these terminologies. We will cover the ADME journey of a drug takes through your body and the key numbers that describe that journey in mathematical way, how drug acts on different receptors at cellular levels, and what makes some drugs very safe. On the other hand, some requires careful monitoring, and we'll discuss about major classes of modern drugs and two real examples case studies involving statins and imatinib, and finally we will see a few PKPD classifications of drug. So this is what we're gonna cover today. This is the roadmap what we are gonna discuss. So firstly we'll discuss about pharmacokinetics. Also we can simply call it as PK. We will learn today ADME and parameters that quantify it. And secondly, we'll learn pharmacodynamics. We will learn what is efficacy, potency, therapeutic index, and therapeutic window, and receptor theory. And thirdly, we'll learn about drug classes and two case studies involving that. And finally, we will look about few drugs in drug bank profiles, and we'll see target mechanism ADME comparison of Metformin, Aspirin, and Atorvastatin. So to begin here, we will discuss about pharmacokinetics and ADME, the journey of a drug. So this is the sequential roadmap. Firstly, if you take a drug, this is what happens. So what I said earlier was pharmacokinetics, what your body does to a drug. So firstly, your body, it absorbs the drug, then it distributes the drug, then metabolize, and then finally it excretes the drug. So this is the ADME journey of a drug. So firstly we'll discuss about absorption. So absorption is nothing but the drug gets from where you took into your bloodstream. So comparatively, if you take a drug through oral and IV, an IV injection skips the absorption entirely. Why? Because it's already present in your bloodstream. So there is no requirement of absorption as compared with the oral dosage form. So which is why IV drug acts fastest and are defined as 100% bioavailable. A swallowed tablet, by contrast, has to survive stomach acid, cross the intestinal wall, and then survive the first pass metabolism. First pass metabolism is nothing but if you take a drug, it changes, it transforms in the liver. So that is what it means. Simply means first pass metabolism, which is why oral doses are often higher than the IV doses of the same drug. So the same drug, if you take orally, the quantity is more required as comparative with the IV route. And coming to sublingual route like nitroglycerin under the so sublingual is kept under the tongue, right? And inhaled routes like asthma inhalers tend to act faster than the oral because they bypass the first pass effect entirely. Even simple things, whether you have eaten food, your stomach acid pH, or how fast your gut is moving, can speed up this process. It may slow down or how much of drug actually gets absorbed. So this is what absorption means. So let's go to the next one, distribution. So distribution is how the drug spreads from bloodstream into the tissues. So it depends on blood flow. Organs like brain, liver, and kidney gets drug quickly, while fat and bone it's very slowly. So which is why some drugs can accumulate in fatty tissue over time. It also depends on lipophilicity or fat solubility, which determines whether a drug can cross the barriers like blood brain barrier, critical for anything meant to act on the brain like anesthetics or antidepressant. And it depends on plasma protein binding, since only the unbound free fraction of drug is actively active and able to leave the bloodstream. This matters clinically too. Two highly bound drugs given together can compete for the same binding sites, pushing more of each into their active free form, which is a classic mechanism behind dangerous drug interactions. This is also where a concept called volume of distribution comes in. It tells us whether a drug's safety stays in mostly the blood like warfarin or spread widely into the tissues like chloroquine. So this is all about distribution. So basically it means drug spreads from blood into tissues and organs. So coming to the third one, metabolism. So it is nothing but it is a chemical transformation. So it is changing your drug entirely. So this takes mainly in liver through various enzymes like cytochrome 450. It is a most essential enzyme which is helpful in metabolism various drug. Around 90% of the drug it is metabolized by this enzyme, and other enzymes like cytochrome 3A4 and cytochrome 2D6, the workhorses responsible for metabolizing the majority of prescription drug. As I said earlier, some drugs are actually like prodrugs, so they are inactive when you're taken, but after metabolism it converts them into their active form, like example like codeine converting into morphine to produce pain relief. Genetic variation in this enzyme is also why some people metabolize drug faster or slower than others. You may have seen the same drug which is given to two different individual, the drug effective in some individual and in some individual it is not effective as compared. So some people are fast metabolizers, some are slow metabolizer, and this is the entire basis of the field called pharmacogenomics, which gives dosing to a person on based on genetic profile. So the last stage of our PK is excretion. So finally, after all these three stages, it undergoes excretion. So this is how the drug and its metabolites leave the body, mainly through kidneys and secondly through bile and feces. Sometimes with drug being reabsorbed from the gut back into the blood in a cycle called enterohepatic recirculation, which can extend how long a drug stays active. Kidney functions directly affects how fast a drug clears. So basically, if a person has very healthy kidney, so the excretion process is faster. But on the other hand, a person with disease can slow up this process. So which is why doses are often adjusted for patients with kidney disease. So that's the full ADME cycle in. So we learn the key parameters of pharmacokinetics. So let us discuss now. We are gonna quantify that journey using concentration time curve. So this is the concentration time curve. As you can see here on the x-axis, you can see time, and y-axis you can see plasma concentration. So we'll go under different terminologies and what it means. Firstly, we'll discuss about Cmax. So Cmax is the peak concentration of a drug reaches after a dose. So suppose if you have taken a oral dosage form, right? You have taken, and after sometimes in your bloodstream the maximum concentration is observed here. So after taking 0, you can see here 0, the concentration has increased, and after two and a half an hour you can see this is showing a maximum concentration in your bloodstream. So it means Cmax. So at this point there is maximum drug concentration in your blood. And coming to the next terminology, which is Tmax, so it means it is a time taken to reach the peak. So you can see here, this is the Cmax, this is the concentration. So time taken to reach this concentration is called as Tmax, simply to put in. So next one is half life. So it is also called as T half. Is it is a time it takes for the blood concentration to drop by 50%. This single number tells how often to a dose a drug with a short half life like some antibiotics might need dosing every 6 hours, while a drug with a long half life like some drugs such as statins can be dosed once a day. It also tells us roughly how long it takes to reach a steady state when starting a regular dosing schedule, and roughly how long it takes to fully clear the body after stopping. In both cases about 4 to 5 half life. So if the concentration is decreased in every half life. And the last one which we are going to discuss is bioavailability. So F, we are going to use this simple to describe bioavailability. So it is a fraction of a dose that reaches systemic circulation unchanged. So IV drugs are 100% by definition, right? So it is directly in your bloodstream, so it shows effect. But on the other hand, oral drugs are almost always less due to incomplete absorption and first pass metabolism. So if a drug has 50% oral bioavailability, you will need roughly double oral dose to match the effect of the IV. So suppose for IV there is 10 mg required, right? But the oral bioavailability of the drug is 50%. So to compete with the IV, you need, if you are taking 50 mg in IV, you need 100 mg for oral route. So that is how you can compete with the IV. So we'll see a quick recap of all this terminology. So absorption, it gets in, distribution spreads it, metabolism transforms it, and excretion removes it. So Cmax is the peak, Tmax is the time to the peak, half time is the time to drop by half, bioavailability in is the fraction absorbed. So I think we are cleared with all this terminology and what it means. And now, pharmacodynamics. So we'll discuss about efficacy versus potency. So a lot of you may be confused between what efficacy means and potency means. So potency is nothing but amount of drug needed to produce a given effect. A more potent drug reaches the same response at a lower dose. And efficacy, it is the maximum effect you can give it as Emax. A drug can produce regardless of a dose. Partial agonist has lower efficacy even at saturating dose. So for instance, we'll take coffee. So if you take a small cup of coffee, it wakes you right up. So this is what potency means. You need small quantity to show its effect. So in the graph you can see on the y-axis, this is a drug response curve graph. So on x-axis you can see the dose, and on the y-axis you can see the response. So for example, we have taken two drug A with high potency and drug B with low potency. So you can see here, drug A, it is shifted to left when compared with the drug B, right? So what does it mean? It means drug A is very potent. We need just little bit quantity to show its response. So this is what it means. We'll take a real example. Phenytoin. Phenytoin and morphine. Both are painkillers, right? To but when it comes to the concentration dose which is given, we need phenytoin very less when compared with our morphine drug. Both are used in painkillers, but we need phenytoin in very less quantity when compared with our morphine drug. This is what potency and efficacy means. So let's move with next one, therapeutic index and therapeutic window. So to calculate therapeutic index, we are having this formula you can see on the screen on left side TI. So T50 by ED50. So what does TD50 mean? So TD50 is nothing but dose toxic in 50% of the patients, and ED50 means dose effective in 50% of the patient. So the higher TI means larger margin between an effective dose and a toxic dose, such that a safer drug. So for example, penicillin. Penicillin TI has over the range of more than 100, so wide window, and it is very safe. So because of having TI value of more than 100, it has a very broad therapeutic window. So generally it is considered one of the most safest antibiotic to ever produce. And the next example will go for digoxin. The therapeutic index is very less, so it is narrow window, so it requires monitoring. And warfarin, so warfarin therapeutic index is 2 to 3, so you can see here it is very low therapeutic window, so it needs frequent INR checks in the hospital. So all this drug, because of knowing the therapeutic index, we can monitor whether it is safe or not. You can see here this is a therapeutic window, so this is a plasma concentration level on the left side. So this is a subtherapeutic minimal effective concentration not reached. So once the drug is given here in the initial point, it goes right up a different time duration, right? So this is the window here, it is considered therapeutic window safe and effective region. And above this region is what toxic level. Once this r- concentration crosses, so it shows toxicity. So that is why some drug requires frequent monitoring and some is not required. And let's go with the next one, receptor theory. So we'll discuss about this. So agonist, partial agonist, and antagonist. So what is agonist? So a drug binds with the receptor and activates it, so it mimics the natural ligand to produce a fully biological response. So basically a drug binds to these receptors and it mimics the natural effect. So next is our partial agonist. So our drug, or we can call it as ligand, binds and activates this receptor but produces submaximal response even at full occupancy. So it does not completely produce full natural biological response, but at some extent it produces the response. And antagonist, so this a drug binds the receptors without activating it, it just blocks this natural ligand or agonist from producing an effect. So in our brain we are having several neurotransmitters, right, like dopamine. So there are different receptors for a dopamine like D2. So what our drug does is it binds on these D2 receptors. So if our drug binds on these receptors, there is no emptiness or no space for our natural neurotransmitter dopamine to bind on this region. So this is what happens, it blocks our dopamine without directly affecting on dopamine, just occupancy on the receptors. So we'll discuss about few classes of our drugs. Firstly, small molecules, biologics, and peptides. So what is small molecules? These are synthetic drugs which are below 900 Daltons. So these are chemically synthesized. Often it is given orally, bioavailable, crosses the membrane easily. Examples such as statins, such as atorvastatin, statin drugs, aspirin, and imatinib. And biologicals. Biologics are large proteins. It is produced in living cells like monoclonal antibodies, enzymes, hormones, given by injection or infusion, highly specific targets. So this is produced by the living cells, right? So peptides, these are short amino acid chains. They're having intermediate size. So this mimics natural signaling molecules such as insulin. For diabetic patients, insulin is given, right? These are peptides generally. So GLP-1 agonist. So these are generally in injectable forms. So let's see about rule of thumb. Small molecules are chemically synthesized and usually given in oral. So this is what we discuss about small molecules. And biologics and peptides are typically injected because they are broken down if taken by mouth, right? So you might have seen. So insulin is not available in oral dosage form. It's only available in intramuscular, right? So once what happens if we take insulin through oral? So generally it breaks down by our stomach acid, that's why it is not available in our in oral dosage form. So I have taken two case study to discuss its mechanism of action and an example how it works exactly. So Let's discuss about statins. So the mechanism of action of this drug is inhibiting HMG-CoA reductase. So firstly, HMG-CoA reductase is a it increases the LDL level. So basically, what we want to do is top these levels and to decrease LDL levels. So if we give our atorvastatin drug, which is a classic example of statins, so HMG CoA, statins blocks this or HMG CoA reductase and decreases the mevalonate, and drastically this leads in decrease in cholesterol synthesis in the liver. So it blocks the LDL receptors and there is decrease in LDL levels in the bloodstream. So this is the mechanism of action of statins. So it HMG CoA reductase catalyzes the rate limiting step in cholesterol biosynthesis. Statins are competitive inhibitors of this enzyme and lowering hepatic cholesterol, right? So this leads in reduced intracellular cholesterol up, regulates LDL receptors and increasing cellular clearance of LDL from the blood. So this is the pharmacokinetic highlight of our atorvastatin drug. So absorption, so given in orally, it undergoes first pass hepatic metabolism extraction, and it is mainly metabolized by cytochrome 3A4 enzyme. This is the main drug interaction, and the half life of our atorvastatin drug is 14 hours, and active metabolites extend effect. So once this our enzyme converts our atorvastatin, metabolites also shows an extend effect, right? And clearance of our drug is primarily from fecal and biliary. And the next drug, it is Imatinib. So Imatinib targeting the BCR-ABL fusion protein. So this is Philadelphia chromosome and BCR. So this is the roadmap of its mechanism of action. So Philadelphia chromosome, BCR-ABL fusion protein or tyrosine kinase. Through this mechanism, Imatinib binds ATP binding sites, right? And this leads in blockade of kinase activity, and it this leads in treatment of leukemia cell proliferation halted. So this is the mechanism of action of imatinib in CML. A chromosomal translocation creates the constitutively active BCR ABL tyrosine kinase, right? So imatinib is a small molecule tyrosine TKI inhibitor that occupies the ATP binding pockets. So adenine tyrosine phosphate ATP. This is what it means. And this blocks the downstream signaling that drives uncontrolled proliferation of leukemia cells. So one of the drug. This is the PK highlights of our drug imatinib. So you can see here ADME of our drug. So absorption of a drug through is orally. It is well absorbed, and bioavailability of this drug is a whooping 98%, which is very high, and distribution is through plasma protein binding and metabolism in hepatic or liver primarily through cytochrome 3A4, and half-life of a drug is 18 hours, which is very good and allowing because of this half-life. So it is taken once in a day, and I have taken few examples from drug bank. These are metformin, aspirin and atorvastatin. So this is PK, and you can see all the details regarding with this drug side by side comparison with the target, mechanism of action and ADME properties. These are data present in our drug bank. You can go through once if you're having academic email. So let's see one by one. So metformin, the drug class. So it is a biguanide, anti-diabetic drug, right? And aspirin, it is an NSAID drug. Atorvastatin, statin, lipid lowering agent. So primary targets, you can see here AMPK, mitochondrial complex 1, and cyclooxygenase COX1 and COX2. You may have heard this, and HMG CoA reductase for lipid lowering LDL. Mechanism of action also it's given here. So absorption of a drug, it is through oral, and distribution, metabolism, not metabolized, excreted, unhinged. You can see over here. It is a full detail or PK of our entire drug. Half life also it's given here. Once you can go through this website and check for yourself. So this is all about pharmacokinetics and pharmacodynamics. So if you have any query, you can just mail at this given mail ID, or you can contact at this given number. And thank you.